Hello everybody and welcome to another YouTube video. In this video, I'm going to be showing you how to make a planet simulation using Python. Now the goal of this is going to be to simulate the orbits of different planets around the sun. We're going to use real astronomical values, so the real mass of the sun, the real distance from Earth to the sun, all of that type of stuff, and we're going to apply the force of gravity between all of the different planets so we actually get an accurate elliptical orbit. Now here it does look like the orbit is circular. It is not. You can see I'm actually writing the distance of the planet to the sun on each planet, so it's changing as we go around the orbit. Well, this is really cool. We're kind of mixing a bit of physics with Python and looking at a cool simulation. Now, I will mention that this tutorial is not designed for complete beginners. You should have some knowledge of Python. However, if you don't know anything about physics, don't worry. I will teach you the different physics we need to know to actually, perform this simulation. It's not very complicated. I myself am not a physics major or a physics guy, and I was able to figure it out pretty quickly. Anyways, with that said, let's go ahead and get into the code after a quick word from our sponsor. Thanks to Backtrace for sponsoring this video. Backtrace provides application monitoring as well as error and crash reporting for games. We've all been there, excited to launch a brand new video game just to be tormented by crashes, bugs, and an overall bad user experience. Backtrace wants to help limit that by providing a platform that gives game developers the best error and crash reporting with the most complete and helpful information. Backtrace works with any platform, any engine, and at any scale, and provides 24/7 monitoring so you can retain more players and get better ratings. Backtrace helps you fix issues fast by providing accurate call stacks, regression detection, querying and analytics, and integration with Microsoft Teams, Discord, Slack, and more. You can get started with Backtrace today and manage up to 25,000 monthly errors with 1 month retention and 10 gigabytes of storage completely for free. Check it out from the link in the description, and thanks again to Backtrace for sponsoring this video. Alright, so let's go ahead and get started. Now I will mention that right here I'm not simulating every single planet. You can easily adjust the simulation to add as many planets as you would like. You can even put something like stars or satellites, whatever. You can put any of that here because of the way we're going to set this up. However, the planets I'm simulating right now are just the 4 closest to the sun. So we have Earth, Mars, Venus, and Mercury. We're just doing that so that we get a nice visual and we can see everything nice and large. If you were to simulate the planets that are much further away from the sun, then you're going to see all of these planets kind of smushed really close to the sun, and then the huge orbits around the sun from the larger planets, if that makes sense, and the planets that are much further away. So this is just a nice visualization. Again, you can adjust this however you like, and I'll show you how to do that. So with that said, let's dive into this. I'm going to close this and just open up a new window here, and we'll start writing some code. Now, the first thing we do actually need to do is install Pygame. So if you don't already have Pygame installed, then just open up your terminal or command prompt, depending on your operating system, and type in the following command, pip install Pygame. If that doesn't work for you, try pip3 install Pygame. If that doesn't work for you, try python-m and then pip install Pygame. If that doesn't work, try python3-m pip install Pygame. And if none of those commands work, I have 2 videos that I'll put on the screen that show you how to fix your pip command. Anyways, I'm going to assume that you have Pygame installed. This is just a 2D graphics library that we're going to use for the simulation. If you don't know Pygame, don't worry, we're going to use very limited features from it, and I'll talk about how all of them work. So the first thing I'm going to do here is just import Pygame, and then I'm going to say pygame .init just to initialize the module. I'm also going to import the math module because we're going to have to use that in this code. Okay, so continuing, since I'm using Pygame, the first thing I want to do is set up my Pygame window. Now to do this, we need to pick a width and height in pixels for our window. So I'm going to say the width, comma, the height in all capitals because this is a constant, is going to be 800, 800. You can make this whatever width and height you want, but I recommend you make it square. And then we're going to set up a window. So I'm going to say win is equal to pygame.display.set_mode. Now this is just going to take in the coordinates for the size of our window. So we're going to pass as a tuple here the width and the height. This is going to give us what's known as a Pygame surface. We're going to call it the window because it's the main window that we're going to draw onto. And we need to have access to this surface to be able to put something on the screen and actually see something moving around. Now what I'm also going to do is just set a caption for this window. So pygame.display.set_caption. Now the caption is just going to be kind of the title of the window. I'll show you what it looks like in 1 second. And for this, we'll just do planet simulation. Okay, perfect. So now that we have this, what I want to do is create something known as the Pygame event loop. Now, this is essentially an infinite loop that's going to run the entire time that the simulation is going. Whenever you're working with some type of game, you need some type of loop that's constantly running. They can keep track of the different events that are occurring. In this case, the only event is going to be moving the different planets, but we need to have some type of loop so that the window doesn't just open and instantly close. We need something keeping the program running. So I'm going to make a function here, and I'm going to call this main. And inside of here, I'm going to make a variable. I'm going to say run is equal to true. Then we're going to say while run like this, and this loop will run while this variable run is true. Now inside of here, I'm going to get the different events that are occurring in Pygame. So I'm going to say for event in pygame.event.get. Now this is going to give us a list of all of the different events that occur. So key presses, mouse movements, whatever. Now when you're coding a more complex game, you're going to handle those different events. However, the only event that we want to handle is when the user presses the X button to close the window. Now that event is the following. We're going to say if event.type is equal to pygame.quit in all capitals, then all we're going to do is say run is equal to false. And then outside of our while loop, we're going to say pygame.quit. So this is literally all we need for the event loop, at least for right now. What's going to happen is we're going to continually run. We're going to get all of the events. If one of the events that occurred was we hit the X button in the window, then we are going to close the window by making run equal to false. Since that's going to exit our loop, we're going to quit Pygame, and then we'll be done. Perfect. So all we need to do here is just call this main function. And now that we do this, we should see a Pygame window pop up, and then we can close it and get out of the program safely. So let's try this. And there we go. We get planet simulation. This is the caption I was talking about. You can see it kind of right here beside the little Pygame logo. Then if I click the X button, we're going to close and we are all good. Okay, we have set up our event loop. Nice. So now that we have done that, I just want to show you how we can draw something onto the screen and kind of update the screen. So let's do that. So at the top of this loop here, I'm actually going to set up something called a clock. Now, a clock is essentially going to make it so that the frame rate of our game won't go past a certain value. I'll talk about why we need this, but the idea here is that if we don't implement some type of clock, so some way to synchronize our game essentially, you're going to run the simulation at the speed of your computer. Now, some people want that to happen. They want it to run super fast if you're on a super fast computer, and then super slow if you're on a super slow one. But ideally for me, I don't care about what type of processor you have. I just want you to run the simulation at the same speed so it looks normal. Hopefully that makes a bit of sense, but we can kind of regulate the frame rate and how many times our game is refreshing. So the way we do that is we say clock is equal to pygame.time.clock, and then we go here and we say clock.tick, and then we put in the number of times that we want this to update per second. Now, this does not mean you're always going to update at, in this case, 60 frames per second. However, this is the maximum that you will be able to update at. So we're saying clock.tick 60. That means we're going to update this loop or run this loop a maximum of 60 times per second to ensure our game's not going too fast. Okay, so now we have our clock. And as I was saying, we want to draw something on the screen. So to draw something, I'm going to use my window right here. And I'm going to say win.fill. And then I need to pass an RGB color here that's going to be the color that I want to fill the entire window with on the screen. So I'm just going to define a color. Let's just go with white for now. And white will be equal to 255, 255, 255. Okay, so that's our RGB value for white. And then I'm going to pass white inside of here. And we should see in a second that we're going to get the screen actually updating. And now it's going to have a white background rather than a black. However, I will show you if I currently run the code, we actually don't get any white on the screen. And the reason we don't get any white on the screen is because we're not updating the display. So what I need to do is say pygame.display.update, not clear. And what this does is actually take all of the drawing actions that we've done since the last update and then kind of paste them and draws them onto the screen. So what I'm doing is every loop, I'm going to fill the background with white, and then I'm going to update the display. Okay, so now if I run this, you're going to see that we get a white background. Now, we don't actually want a white background. I want a black one, so I'm going to get rid of this. I just wanted to show you how we fill the screen. Okay, so let's comment these out for right now. Perfect. So now that we've done this, let's start implementing a planet, because obviously we want to put some planets on the screen. And to do this, I'm going to make a class. So I'm going to say class planet. And inside of here, I'm going to define an initialization. I'm going to say define init. I'm going to say self. We need an X and a Y. Now the X and the Y is going to be the position that we want this planet to be on the screen. We also are going to need a radius. We're going to need a color. And then let me just check if we want to take anything else. We're also going to need a mass for the planets. Okay, so these are kind of the initialization values that we have. So I'm going to say self.x is equal to x. self.y is equal to y, self.radius is equal to radius. Obviously, we're going to have circular planets. Self.color is equal to color. We might want to make our planets more detailed and have multiple colors, but for now, we're just going to go with a single color. And then the mass is going to be the mass in kilograms of this planet. We're going to have to use that mass to calculate the attraction between the different planets and then generate the actual circular orbit, which we'll get to when we start talking about the physics. Now, there's a few other things that we want our planets to have. They're going to have an x velocity as well as a y velocity. So I'm going to say self._xvel is equal to 0, and self.yvel is equal to 0. Now, I'll explain how all of these concepts work in a second, but the idea is we're going to be moving our planet in a circle, and in order to move in a circle, we have a velocity in multiple directions. So we're going to have it in the x direction, which is the horizontal direction, and then in the y direction. And by moving in two directions at the same time, we're able to generate a circle and have kind of, I don't want to call it centripetal force or some centripetal motion, but something along those lines, right? Where we're actually moving in a circle around an object at a constant speed. Okay. Hopefully this is making sense so far. Another thing that I want to do here is I want to have something that says self.sun is equal to false. Now this is going to tell us if the planet is the sun. The reason we want that is because we're going to draw the orbit of the planet moving around, and I don't want to draw the orbit for the sun. So I need to know if it's the sun to either draw it or to not draw it. And then I'm going to have the self.distance to sun. I'm just going to make this equal to 0 right now, and we're going to update this value for every single planet that we have so that we know what its distance is, and we can then draw that on the screen. And then the last thing that I want is self.orbit is equal to an empty list. We're going to use this to keep track of all of the points that this planet has traveled along so we can draw a circular orbit representing, well, the orbit of the planet. Okay. Again, all this will start to make sense as we get into more of these concepts. I'm just kind of setting up all of the initialization values. Now, a few other things that I want to do here is just write out a few constants that we're going to use for our simulation. Now, the first constant we're going to do as a class variable in the planet class, and this is going to be AU. Now, AU is astronomical units, and this is approximately equal to the distance of the Earth to the sun. Now, I want to use AU because it's going to simplify the math that we need to do to calculate the distance between the current planet and the sun and allow us to initialize our planets at the correct AU from the sun, so they're kind of the correct distance away. Hopefully that makes a bit of sense, but 1 AU is equal to, and I just have to copy this from my other screen, 1.49.6 to the exponent 6, which is what this E6 stands for, and then multiplied by 1,000, and I don't actually need these in parentheses, so I don't know why I had it there. Okay, so what this is saying is we are 149,000, I guess this is, 149 million and then 600,000 kilometers. That's what this stands for right here, but we want this to be in meters, so I'm going to multiply it by 1,000 to get the distance from the sun in meters. 1 AU, that's what this is. Hopefully that makes sense. Again, 1 AU is the distance from the Earth to the sun, approximately, and here we're converting this from kilometers to meters by multiplying it by 1,000. Okay, now we also want the gravitational constant. Now this is not negative 9.8, that's the acceleration of gravity. I think it's the acceleration of gravity. I might be messing that up, but it's something to do with gravity. But the gravitational constant is used in finding the force of attraction between objects, which is what we want to do. And G is different than the regular gravity one. It is 6.67 and actually is 4.28 e to the negative 11. Okay, that's great. My autocomplete is working very well there. Nice. Now, the last two things we want here is a scale. Since we're actually going to be simulating the real values here for the orbits, we can't draw them at the position that we have them at. I know that's probably a confusing line, but the idea is if our planet is moving at, something kilometers per second, 7 kilometers per second, 29 kilometers per second, I can't draw my planet at 1,000,000 kilometers in my Pygame window. I need to draw it in a kind of appropriate scale, right? So I'm going to have to figure out what 1 meter represents in terms of pixels in my Pygame scale here, because I'm only working with 800 pixels high and 800 pixels wide. Hopefully this is making a little bit of sense. But what I'm going to do here is say 250 divided by AU is the scale. Now this scale essentially says that 1 astronomical unit is going to be about 100 pixels in my Pygame program. You can look at the math to figure out how that works, but for now I'll leave a comment. We're going to say 1 AU is equal to 100 pixels. Okay, that's kind of the scale that we're going with here. so we can draw things to scale in the window. And then the last thing I want is the time step. And this is going to represent how much of time I want to represent in my simulation, or that I want to simulate is being elapsed. So the idea here is every time I update the frame, I'm going to pass a certain time step and say, okay, I want to look at 1 hour of this planet's movement at a time, or 1 day of this planet's movement at a time. Because I don't want to look at 1 second. It's going to take a really, really long time to simulate. Instead, I want to look at a larger time step. So what I'm going to do is say 3,600, which is the number of seconds in a, what is this? In an hour? Yeah, I think this is the number of seconds in an hour. And then I'm going to multiply this by 24, and that's going to give me 1 day. Okay, so this is representing 1 day. I think that's correct. Yeah, okay, I'm pretty certain that is correct. This would be the number of seconds in an hour, right? If you go 60 times 60, I think that gives you 3,600, and then multiply that by 24, and that is the time step that we're going to be doing the simulation on. So kind of 1 day at a time, we'll be updating the planet. All right, hopefully I'm not confusing you guys too much. I do understand this is a lot. We got to go through a bunch of physics and stuff here to make this work, but there you go. That is a planet. Now, the next thing I want to do is implement a draw method. Now, this draw method is just going to draw the planet on the screen. So what I'm going to do is say self, and then I'm going to take a window that I need to draw this planet on. So the X and Y for my planet, as well as the X velocity and the Y velocity for my planet, is going to be in meters. So the number of meters that I am away from the sun. That's what X and Y is going to represent. So I need to take those values and then draw them to scale, right? Because again, I can't draw like something million kilometers or million meters away. I need to draw it in an accurate scale in Pygame. So this is where the scale is going to come in. I'm going to say that my X is equal to, and then this is going to be the self.x multiplied by my scale. Okay, so it's going to be self.scale, and self.scale is going to be a really, really tiny number that will now take this number and bring it to scale. And then I'm going to say y is equal to self.y, and I'm going to multiply that by self.scale. Okay, nice. Now, one other thing I need to do is make sure that I'm drawing all of this in the center of my screen, because I haven't mentioned yet when we're talking about Pygame, 0, 0 is actually the top left-hand corner. So let me just quickly open the window here. Right here where my mouse is, so top left-hand corner, this is 0, 0. If I go all the way to the right, this would be 800, 0. If I go all the way to the bottom right-hand corner, this would be 800, 800. So rather than having 0, 0 in the middle, which you might be used to, it's the top left. So I don't want to draw my stuff in the top left. I want to draw it in the center. So that means I need to take every single value I have, I need to offset it by the center of the screen so that we draw stuff in the middle. Hopefully that makes a tiny bit of sense. But the way we do this is we say plus, and then this is going to be width over 2, and then this is going to be plus, and then this is going to be height over 2, and those values are right here. Okay, so the width and the height, we could just write 400, but I'm going to do width and height so that if we change the width and the height, this is going to update automatically. Okay, so now we have our X and Y, and now I can actually draw this onto the screen. So I'm going to say Pygame.draw.circle, and then I'm going to pass the window, which is where we want to draw this circle. I'm going to pass the color that I want to draw the circle in, so this is going to be self.color. I'm going to pass the position that I want to draw it in, which is going to be XY. That's the center of the circle. And then lastly, I'm going to pass the radius, so self.radius. Okay, so now we're actually going to draw the circle on the screen when we call this draw method. Okay, hopefully this is all making a bit of sense. Let's now go and actually draw a few planets and initialize some of their constants. So the first planet we probably want to draw is the sun. Could you call the sun a planet? I guess it's a star. Again, not a big physics guy, but the first thing we want to draw is the sun. Okay, so I'm going to say sun is equal to planet, and we're going to pass 0, 0 for its XY. Okay, so 0, 0 right here. For the radius of the sun, we can kind of pick whatever value we want here. We're just going to be kind of randomly picking the radiuses based on the relative mass of the planets. So we want the sun to be the biggest, and what I have in my other program here is 30 for the radius, so we'll go with that. And for the color, I want this to be yellow. So just to make this a bit easier to read, I'm going to define yellow up here. And yellow, actually, how do you even make yellow? Let's look at this. Yellow is going to be 255, 255, and 0. Okay, so that's the RGB value for yellow. Obviously, that's the color we want the sun. So let's now put the color as yellow. And then the last thing we need to pass is the mass. And the mass, I need to look at my cheat sheet here because unfortunately I don't have this memorized, is going to be the following. let me paste this in, 1.98892 times 10 to the exponent 30. And in case you're wondering, this is in kilograms. Again, we're going to use the accurate masses and astronomical units and stuff for all of these planets. Okay, so that is the sun. And for the sun, we're just going to say sun.sun is equal to true. Because remember, we have this property here that says sun, and we're going to make this true so that we don't draw the distance to the sun from the sun, and we don't draw the orbit for the sun, which we don't need. Okay, so now that we have this, let's just see if we can draw this on the screen. So let's go planets is equal to, and let's make a list of all of the planets because we're going to add a few more. And then inside of our loop here, we're going to say for planet in planets, and we're going to say planet.draw, and we're going to pass the window that we want to draw it on, which is win in all capitals. Okay, nice. Now we also need to make sure that we're updating the display, so let's steal this here, and let's put it down there. Okay, nice. So we're saying for planet in planet.draw, pygame.display.update. Let's see if this works. Fingers crossed, let's run the code. Okay, there we go. We get a sun in the middle of the screen. Very nice. That is exactly what we wanted. All right, now the next thing we want to do is draw a few more planets, right? So let's create Earth, Mercury, all of those, okay? So we're going to start with Earth. We're going to say Earth is equal to planet. Now the Earth is actually going to be -1 multiplied by planet with an all capital .au. This is going to be the distance from the sun, so we're going to put that as the x coordinate. And for the y coordinate, we're just going to make it 0 for right now. The color of the Earth is going to be blue. We'll write that RGB variable in a second. And then the mass of the Earth, actually, sorry, we need the radius as well. Let's put the radius first. What was the radius of the Earth? I had 60 in here as the radius. And then the mass of the Earth is this number. Let me copy it in. 5.9742 times 10 to the exponent 24. Okay, that's the mass of the Earth. Now, I will actually mention here before I continue that there is a great article. I'm going to open it up so I can show it to you guys. Let me get it on my Google Chrome here. That I'm actually inspired by making this program that has all of these values already. So this is the article. I'll leave it in the description. But it essentially implements the same thing we're going to implement here in Turtle. Now, I didn't want to do it in Turtle because Pygame is a lot better and it's a lot faster. But if you look here, all the values that I'm using are just coming from here, right? So like the Earth mass, the Earth distance, -1 times AU, the sun mass. Just wanted to give credit to this article. I'll leave it in the description. Anyways, enough of that. We have the distance to the sun, which is this. We have 0, 16, blue. This is the mass. And I think that's all we need for the Earth right now. Let's now put Earth inside of here and see if when we draw it, we get it in an accurate position. Okay, so let's run this. And we get blue is not defined. Okay, I forgot to do that. Let's define the color blue. Blue is going to be equal to, and then I want kind of a nice light blue. So I just picked one of these before. It's going to be 100, 149, 237. This is the RGB value for kind of a lighter blue. If you just wanted it to be regular blue, then you could go 0, 0, and then 255. That give you a nice dark blue. Okay, so let's run this now and see if this works. And there we go. We get the Earth, which is, 1 AU away from the sun. Hopefully that makes sense, but this is how the scale is working. We put it at -1 AU, which means we're going to the left. If we put it at 1 AU, we would have gone to the right. Doesn't really matter where we start it. And there we go. Okay, so now we have the Earth. The next planet that I want to do, let's look here, is going to be Mars. So let's say Mars is equal to a planet. Now, the distance for Mars is going to be this. Let me just copy it in. It's going to be -1.524 times planet.au. Again, we're going to put its y coordinate at 0. The radius of Mars, it's much smaller than Earth, so we're going to go with 12. It's going to be red, which I'll define in a second. And then the mass of Mars is a little bit less than Earth as well. So that's going to be 6.39 times 10 to the exponent 23. Now for red, we need to define this. Now again, I wanted kind of a nice looking red, so I picked a custom RGB value here. And this value is going to be 188, 39, and 50. Okay, and now we have Mars. So now that we have Mars, we're going to put Mars inside of here. And we should now draw Mars at the appropriate scale. So let's look at this, and we see the Mars over here. So notice that Mars is kind of right by the border. I'm fine with that, but if you wanted to move everything in closer, then what you would do is reduce this number right here. So rather than doing 250, you would do something like 200. and you're going to notice this is going to move us in a little bit closer. So that's kind of how you can mess with things. Just make the number here smaller if you want everything to get closer to the sun. Okay, so we'll go with 250 AU for now. All right, so now we have Mars. Let's do our other planets. So the other planets we have is Mercury. This is going to be equal to planet. This distance, this is the closest one to the sun. My understanding is, at least. This is going to be 0. We're going to have to make this smaller, so we're going to go 0. The color is going to be dark gray, which we'll implement in a second. And then the mass, let me just copy this in, is going to be 0.330 times 10 to the exponent 24. If we want it to be consistent, we could go 3.30 times 10 to the exponent 23. That'd give us the same thing. Okay, so let's implement dark gray now. So let's go up to colors. Dark gray is equal to, and then what did I have dark gray at? Let me just look here. This is going to be 80, 71, no, 78, and 81. Again, you mess with these colors if you want. I'm just picking some custom ones so they look a little bit nicer. Okay, so now we have Mercury, so let's put Mercury in here, and we can just go right on to Venus, which I believe is the next planet. So we're going to say Venus is equal to planet. Its distance is going to be 0.723 times planet.au. In case you're wondering, planet.au is referencing this right here just because it's inside of the planet class. Okay, so planet.au, we're going to have 0. This is a little bit larger, so we're going to go 14. The color of this will just be a regular white. And then the mass is going to be this. Let me copy it in. 4.8685 times 10 to the exponent 24. Okay, let me zoom in so you guys can read that a little bit better. Let's now put Venus in the list. And let me go ahead and run this and see if we're getting all of our planets. Okay, nice. So there we go. And I've just put the planets on different sides. Again, you can kind of put them wherever you want. Doesn't really matter. We could put them all on the same side and have them move at the same time. I'm just staggering them a bit. Maybe some of you will have issue with that based on your physics knowledge, but this is what we're going to do for right now. Okay, there we go. We have all of our planets. So now that we have all of our planets, the next thing we need to do is start moving them. Now, moving them is complicated, but again, as I mentioned, we're going to be moving them by their x velocity and their y velocity. But we need to determine what those velocities are, and those velocities are determined by the force of attraction. So essentially the force of gravity between the different planets. All right, so I'm going to start explaining the math that's going to go on here to actually move the planets around the sun. And before I can do that, I just want to give you a general understanding of gravity and how planets actually orbit around the sun in case you're unfamiliar. So the reason why when we jump up, we fall down, or when we throw a ball up, it comes down is because of gravity. Now, we all know gravity, but gravity is relative to different objects, okay? So all objects are actually attracting one another, and the force of attraction that they have on one another is based on the mass of those objects. Now, this only really becomes relevant when you have very, very massive objects like planets. So when we're talking about something like Earth, this is a massive body, right? It's something like, 6 multiplied by 10 to the exponent 24 kilograms, or whatever the number is. It's a very, very massive body. So relative to our mass, which is maybe 60 kilograms, 70 kilograms, 80 kilograms, whatever it is, it's way, way larger. So it actually exerts a massive force on us that pulls us downwards towards the Earth. Now, what actually determines the strength of this force is the distance from us to the center of the Earth. Hence why when you go up in space, you have zero gravity because you're much further away from the Earth. Now, all objects, again, exert forces on each other, and those forces depend on the two masses of the objects as well as the distance of the objects. But if you're just naively looking at this equation here, which is actually the force of attraction, you'll see that the distance between the center of the two objects is the most important when it comes to what type of force you're going to get, because it's r squared. So the further away you go, exponentially, the less gravity you're going to have. The closer you get, exponentially, the more gravity you're going to get. Now, again, I'm not a physics major, so take everything with a grain of salt here, but that's the basic understanding of gravity. Now, when we're talking about planets, we're talking about multiple massive objects that are moving around each other. So when we talk about an object like Earth here, right? The Earth is moving at a constant velocity. Well, not necessarily constant, but it's moving at a relatively constant velocity around the sun. Now, what forces it to move around the sun is gravity. So the Earth is already on a trajectory moving in the x direction, okay? So it has some speed going in the x direction, and then there is a force pulling it towards the sun. That force is gravity, or the attraction between the Earth and the sun. Now, the reason why there's an attraction is because the sun is much, much larger than the Earth. If the Earth was larger than the sun, then the sun would be orbiting around it. Great example if you think of the moon, right? The moon is much smaller than the Earth, it's very close to the Earth, and so it orbits around the Earth, okay? Hopefully this is making a little bit of sense. But the idea is that you have some force, and that force essentially is causing the Earth to move around the sun. And the reason why the Earth doesn't just shoot directly towards the sun like we shoot directly down on Earth when we jump up is because it already has momentum moving in another direction. And so there's multiple forces affecting it, causing it to go in an orbit. Again, very simplified explanation of what's going on, but hopefully that makes a bit of sense. Now, the reason I'm saying this is because we have multiple planets that are orbiting around the Earth, right? Maybe we have another planet. I know I probably shouldn't have drawn it in blue, but the point is there's a distance between these two planets, and they also have a force of attraction on each other. And that's why you're going to have different orbits and different speeds based on the location of other planets and kind of their orbital trajectory. So if you have two planets here as well as a planet here, well, this guy's still orbiting around the sun because the sun is much larger than him, but he's going to be orbiting slower than the Earth is because he's not as close. However, the Earth is going to be attracting or having some force of attraction on this planet, and this planet's going to have some force of attraction on the Earth, and so you need to take that into account when you're actually calculating the different orbits of the planets. All right, I know this is a lot, very, very math and physics heavy here, but the idea is every single object exhibits some force on each other, and we need to calculate what all of those forces are when we are actually determining the orbit so that we are going to be orbiting appropriate to where the other planets are. So we can't just calculate the force to the sun. We need to also calculate the force to the other planets, and that's going to give us a somewhat elliptical orbit as well. Okay, hopefully this makes a little bit of sense. Now let's talk about how we actually do this. So as I kind of already hinted at, if you look to the left of my screen, you can see that I have the equation here for the force of attraction between two objects. Now, this force is the straight line force between two objects. So let me just move the Earth a bit here so I can explain kind of what I mean by that and why we need to do a little bit of trigonometry. So let's say we have the Earth over here. This, we'll say, is the force of gravity or the force of attraction between the two objects. Now, to calculate this is fairly simple. We just need to first calculate the distance between the two objects, which we can do. We then need to know the masses, which we already know, and the gravitational constant, which we know as well. So let's say we know the force. Well, if we know the force, the issue is it's giving us the straight line force. We want to break this force into two components so that we are able to move the Earth in an x direction as well as a y direction. So we need to kind of understand this, that it's giving us the straight line force, and we need to break that force into x and y components so we can actually move the Earth around the sun in both the x and the y direction. Now, this is the same way that we're going to calculate the distance. It's very easy for us to actually find the distance because we're looking for, let me just redraw all of this right here. So this is going to be r. We don't know what r is, but we know what the y distance is and the x distance is between these 2 points. Because for both these points, we have an x and a y, right? So we have like x2 and y2. So if we know both of those points, we can calculate the difference in x and the difference in y. And then to figure out what r is relative to our right triangle here, what equation do we use? Well, Pythagorean theorem. I know I completely butchered that, that name, but it's going to be x squared plus y squared. Take the root of that, and that's going to give us r. Okay, so we are able to calculate r, then obviously we can take the square. So once we do that, we calculate the distance, then we're going to calculate the force, and then we need to go in the opposite direction from the force back to the x and y components. Okay, so let's redraw this. So now let's say we know the force, okay? And again, we need to split this into x and y. So we need to have, I guess, fx and fy. Now, the way that we do this is we need to calculate the angle here, theta, because if we have any two aspects of a triangle, so if we have one side length and an angle and it's a right angled triangle, we can calculate any other angle or any other side length, right? That's just a property of a right triangle. So we know f, and we should know this angle, and the reason we know this angle is because we know x and we know y. So the way we calculate this angle is we take the arctangent, so the tan inverse of y over x. Now, to derive why this is going to give us the angle theta, let's look at the equation of tan of theta is equal to, and then this is going to be the opposite over the adjacent. Now, I like to remember this as TOA, okay? But this is the equation, this is a property of a right triangle. So if I have tan theta is equal to the opposite over the adjacent, and we're talking about this right here, the opposite side length is y, the adjacent side length is x, and so we can kind of sub those values in, right, and we get y and x. If we want to isolate for theta, we need to take the inverse tangent, so that's what we do. We take tan inverse of y over x, that gives us theta. Okay, so now that we know theta, we can now use theta to calculate what the F force component is, or the X force component is, as well as the Y force component. So to do that, we need to use some other properties. So we have a property, it is let me write this property. So ka toa, this is the way that I always remember these, but we can say that the sine of theta is equal to the opposite over the hypotenuse. And since we're looking for the opposite, which is Fy, we can say sine of the angle theta, which we know, is equal to the f of y over h. H is f, we know f, and we're able to find what f of y is by just isolating for f of y, so multiplying f by sine theta. And then same thing if we want to find what fx is, we can say fx is equal to, this is going to be the cos of theta multiplied by f. That will give us the fx component. And then once we know the x and y velocity, we can very easily move this around the sun. All right, math lesson is now over. Hopefully, I didn't confuse you too badly. Again, I'm trying to squeeze in what is probably taught in an entire year of grade 12 physics in about 10 minutes. But that is the math that we need to understand to be able to move these objects around. Can't really make it much simpler than that. If you don't understand basic trigonometry, then I'm sure this was a lot, but you can kind of just trust the properties that I showed you here, and I will show you how to implement them in code. If you don't understand, totally fine. You can still follow along and you will have a working simulation. With that said, let's go back to the code. All right, so I'm back in the code, and it is time to do some math inside of code. Now, I know we just did a lot of math, but now we're doing it in code. Hopefully that gave you an explanation of what I'm about to write here. So I'm on my planet class, and I'm going to write a method that will calculate the force of attraction between another object and the current object, okay? So I'm going to say define attraction like that. I'm going to take in self, and I'm going to take in another object. Now, the other is going to be another planet, okay? So the first thing I'm going to do is say that my other underscore x, other underscore y is equal to other dot x and other dot y, okay? Now, the first thing we need to do here is we need to calculate the distance between the current object and the other object. So let's do that. We're going to say the distance in x is equal to, and this is going to be the other x minus the self.x, okay? And then the distance in y is going to be equal to the other y minus the self.y. Now, it doesn't matter if you take the self.x and subtract it from other.x, it doesn't matter what way you do it. It's going to give us the magnitude, which is what we want, sorry. Because once we take the square of both these values, we're going to get a positive value no matter what. So I have the distance x and the distance y. Now I'm going to say distance is equal to, and this is going to be the math.sqrt of the distance x to the exponent 2 plus the distance y to the exponent 2. Okay, let me just check and make sure I haven't messed this up yet. Looks good. We have found the distance, okay? Now, the first thing I'm going to do is I'm going to say if the other dot sun, then I'm going to say the self dot distance to sun is equal to distance. Now, the reason I'm doing this is because if the other object that we're calculating the force of attraction with is the sun, I just calculated the distance to the sun, and I just want to update the distance to sun property here so that I can use that when I actually want to draw the distance to the sun on top of the planet. Again, we're just checking, is the other object the sun? If it is, okay, we know the distance, so let's just plug that in and save that value inside of the class. That way we're not recalculating it later on, we already have the value. Okay, so now that we've done that, we need to calculate the force of attraction. So we're going to say the force, I think it's force, is going to be equal to self.g. We're going to multiply this by our self.mass, multiplied by the other dot mass, and then we're going to divide this by the distance to the exponent 2. And why did I write it like that? It's going to be distance to the exponent 2, and I think that's good. Okay, now we don't need to do any parentheses because these have the same order of operations, and exponent to the exponent 2 is going to happen first anyways. Okay, so this is how we calculate the force. Now remember, this is the straight line force. We need to break this force down into the x and to the y component, which is why we had to do all of that trigonometry. So now we need to calculate the angle theta. So we're going to say theta is equal to, and then this is going to be the math.arctangent of, and it's actually going to be here the distance y over the distance x. Now, the reason I'm doing a tan 2 is because this is a special function in Python that's going to take the y over the x and then give us the angle associated with it. So make sure you use a tan 2 from the math library. If you just use a tan, that's not going to work. You need a tan 2, okay? So math.atan, distance x, distance y. Now we know the angle theta. Now that we know the angle theta, we can calculate the x velocity and the y velocity. So we're going to say, or sorry, not the x velocity, we're going to calculate the x force and the y force. So we're going to say the force x is equal to, this is going to be math.cosine of theta multiplied by the force, okay? And then the force underscore y is going to be equal to the math.sine of the theta multiplied by the force. Okay, and then we're going to return from here the force x and the force y. Okay, let's break down what we did here. I understand this is probably a little bit confusing still. We first calculate the distance between the two objects. There we go. We have the distance. Great. Then what we're going to do is determine if the other object is the sun. If it is, we're just going to store that distance in a property here because we want to know what that value is. Now, after that, we want to calculate the force of attraction. So this is the force of attraction here. It's F equals m, lowercase m, over r squared multiplied by the gravitational constant g. Okay, so that's what we're doing. So self.g times mass multiplied by other mass over distance squared. Okay, then we want to break this distance down into the two components. So the force into the x force and the y force. So we first need to calculate the angle. So we say the math.arctangent 2 of the distance y over distance x gives us the angle that we want. Then we're going to say the force x is equal to the math.cosine of theta multiplied by force. And the force y is equal to the math.sine theta multiplied by the force. Now remember here that all of these distances and all of these forces are real distances and forces. These are actually the distances and the forces that you would see. I mean, it's an approximation in the real solar system. So I'm not using really small pixel values in Pygame. I'm using massive, meter per squared, kilogram squared values. Whatever the units are of these forces, I'm actually using the correct numbers, like the large 2-scale numbers. I just want to make that clear here because like if we were to print out what x were and print out what the force were, you would see really, really massive numbers because that's actually what they are in the real world because we're trying to do a simulation here. Okay. Anyway, so we have attraction. Now that we have the force of attraction, what we need to do is actually update the position of each planet based on the force of attraction between every single other planet because we can't just do it from the sun. We need to look at all the other planets as I was discussing kind of in the whiteboard section. So what I'm going to do is make a method here. I'm going to say update position, and this is going to take in self and planets, okay? So what we're going to do is loop through all of the planets. We're going to calculate the force of attraction between the current planet and all of the other planets. We're then going to calculate what the velocity needs to be for these planets. Then we're going to move them by that velocity. So we're going to say the total force in the x direction is equal to the total force in the y direction, which is currently equal to 0. And we're going to sum all of the forces together from all of the planets. So we're going to say for planet, in planets, we're going to pass a list of planets here. That's what we're taking in. We're going to say if self is equal to planet, then continue because we don't want to calculate the force with ourself. In fact, that would just give us a 0 division error because the distance between ourself and ourself is 0, right? So we can't do this division with the arctangent. Or, sorry, with the distance squared, that would give us an issue. Anyways, continuing. Now what we're going to do is say that the force x, force y is equal to, and this is going to be the self.attraction to this planet, okay? So again, for every single planet, we're going to calculate the force x and the force y that it's exerting on this planet. We're going to say self.attraction is equal to planet. That's what's doing the calculation here. That gives us the fx and fy. And then we're just going to sum these two variables or add to these two variables. So self.x fx plus equals fx and total fy plus equals fy. Okay, so now that we know what the total force is that's being exerted on us in the x and the y direction, we need to use these forces to actually calculate what the velocity of the planet's going to be. All right, so the way we calculate the velocity here is we're going to say that the self.x_vel is equal to the total fx divided by the self.mass multiplied by the self dot, and then this is going to be time step. Now, I'm going to explain how this works, but this is using kind of the famous equation F equals ma. Okay, so we have this equation, F equals ma, and this stands for the total force is equal to the mass divided by the acceleration. Now, you can use this to solve for the acceleration, which is what we're doing here. So we're saying the acceleration is equal to F over m. So I'm taking my total Fx and my total mass, right? I'm dividing those to get the acceleration. Now, the thing is, I'm going to be adding to this. So I'm saying self.xvel plus equals. So the way this works is I'm increasing my velocity by my acceleration multiplied by the time step. Now, there's another equation that has to do with time and acceleration to equal velocity and all those kinds of things. Anyways, the point is, though, since we're simulating this over a period of time, we're going to take the time step, which is right here, which is 1 day. We're going to multiply that by whatever the acceleration is. And then we're going to take that value and add that to the current velocity. Now, why this is going to give us a perfect elliptical is because as soon as we start going to the left or to the right of the planet and the distances and the angles change, our force is going to be either negative or positive, saying that we're going kind of right or we're going left or we're going up or we're going down. So by doing a total summation of all of these forces, what ends up happening is we go in a complete circle, because by the time we get to a certain point in the orbit, the velocity is going to be changing and either getting more positive or more negative, moving us to the left or to the right. Hopefully that makes a tiny bit of sense, but the point is we're going to constantly add this, and you'll notice that we're not going to go faster. We're just going to change in directions, because what's going to happen is x velocity is going to be decreasing while the y velocity is increasing when we're at a certain point in the circle, and then that's going to continually change and change directions as we move around. So you'll see when we start running this, but that's how this works. Now we do the exact same thing with the y. So plus equals the total Fy over the self.mass. Okay, and then multiplied by the self.time step. Okay, so now that we have that, what we need to do is just increment the x and the y, because this is just the velocity. So from acceleration, you get velocity. From velocity, you get displacement or distance, which is what we're now going to do. So we're going to say self.x, and then this is going to be plus equals self.x underscore vel. And then we need to multiply this by the time step as well. And then we're going to say self.y plus equals, this needs to be self.yvel multiplied by self.time step, and then let's fix this to be self.xvel. Okay, and then lastly here, we can actually say the self.orbit and then dot append, and I'm going to append just a tuple here, which is going to be self.x, self.y, and yeah, I think that's actually good for the orbit. Okay, so let me break this down one more time. What we're doing is we're getting the total forces exerted on this planet from all other planets that are not itself. We are then going to figure out what the x and the y velocity is using the equations I described. Then we are going to update the x and y position by using the velocity. We need to multiply by the time step to make sure we're moving in the accurate amount of time here, okay? And then we have self.orbit dot append, and we're appending the x and y position that we're currently at, so that now we can draw the orbit for this planet, which I'm going to do in a second. Okay, so there we go. We actually have all of the hard stuff done. Now we just need to call the update position method here on all of our planets, and you'll see that they'll start moving around the screen. So I'm going to go to right before planet.draw, and I'm going to say planet dot, and then this is going to be update position, and I'm just going to pass to it planets. Okay, and that's actually all we need to start moving the planet, and let's just run this now and see if it works. Okay, so let's see. And we can see that our planets are moving, but we're getting a bit of an issue, and I'm going to explain why that happens. So first of all, the reason why we were seeing our planets like thousands of times on the screen is because we need to refresh the screen by kind of redrawing a background on top of it before we draw everything again. So what's happening right now is we're continually drawing the planets, but we're not drawing anything on top of the old planets, and so we keep seeing the old planets. So all I need to do here is say win.fill, and I'm just going to put inside of here 000, which is just the color black. And now if I run this, you're going to see that the planets just zoom towards the sun. Now, the reason they're zooming towards the sun is because they don't have a velocity in the y, or sorry, in the x. Is it the x? No, it's in the y direction. So currently, right, if I run this, you see that they just zoom right towards the sun and then keep going. The reason they're doing that is because we don't have another velocity. And that's what would happen if they weren't already moving in another direction. So we need to apply an existing velocity in the y direction to these planets so that they will be moving around the sun, so that the force attracting them to the sun causes this kind of centripetal motion or the circular motion around the planet. I know this is there's a lot of physics. I wasn't actually considering how many physics I would need to explain here. But the idea is for all of these planets, they need some starting velocity in the y direction. Otherwise, the only force being applied is directly x because of kind of where the planets are placed and the fact that we're just going straight down towards the sun. That's the only force being applied currently because we don't have another velocity. So let's apply the other velocities. I'm just going to copy them in from my other screen. So this is the Earth velocity. I'll pause so we can read them all in a second. This is the Mars velocity. This is the Mercury velocity. And then this is the Venus velocity. Okay. So the Earth y velocity is 29.783. This is kilometers per second multiplied by 1,000, which gives us meters per second because that's what we're using. Excuse me. The Mars velocity, 24.077 multiplied by 1,000. Again, this is meters per second. So kilometers, then we convert to meters. 47.4 for Mercury, and then negative 35.02 times 1,000 for Venus. Now you'll notice that for some of these, we have positive and negative, or not positive and not negative, right? Like we have a negative planet AU moving us to the left, and then we have a positive y velocity. Then for this one, right, we have a negative and positive, and then here we have a positive, and this actually needs to be negative to make sure that it's going to be moving in the correct direction. So if you have one that's positive, the other one needs to be negative so that they're all moving in the same direction, vice versa. Hopefully that makes sense, but you'll see here when this starts running. Okay, so let me actually just run this now, and we should see that they orbit. So let's have a look. Okay, so there we go. Now we have an orbit. Obviously, it doesn't look as cool when we're not drawing the orbits, but notice that they're all moving in the same direction, and obviously the ones that are closer to the sun are moving faster. Perfect, so the simulation seems to be working. Okay, so let's now draw the orbits around. And the way that we're going to do that is we're going to use all of the points that we're storing in this orbit list, because every time that we call this, we're going to add a point to the orbit list, and we're going to draw them. So what I'm going to do is add something here and say, for point in self.orbit, and I actually want to draw this, I'll draw this before I draw the circle. I'm going to say xy equals point, and then I'm going to say x is equal to x multiplied by self.scale, and then this is going to be plus width over 2, and then I'm going to say y is equal to y multiplied by self.scale plus height over 2, and then we are going to actually store these in an updated points list. So we're going to say updated points is equal to this. Updated points dot append point. And then we're going to draw all of these points as a line. So we're going to say Pygame dot draw dot line. And is it lines? Let me just have a look here to see actually exactly what we need to do. So this is actually going to be lines, sorry. We're going to pass win. We're going to pass self.color. We're going to pass false, which means this is not an enclosed line, so we're not going to draw an ending line, essentially. And then we're going to pass the updated points, and we'll pass a thickness of 2. Okay, let me explain what I did. I understand I kind of just went through this without any explanation. So what I'm doing is I'm getting a list of updated points, which are going to be all of the XY coordinates to scale, right? Because I need to get them to scale, otherwise I can't draw these properly. So I take them, I do what I need to do to get them to scale, exactly what I did right here. And then I update, I make a new list here, updated points, and append, sorry, not the point, the new XY that I made right here. Okay, then I'm going to draw lines. Now what this does is it takes a list of points, which is right here, and it essentially just draws a bunch of lines between the different points, and it doesn't enclose them because I passed false. Now this is the thickness that I want to draw the lines, which is going to be 2 pixels. Now, one thing I do need to do is just put an if statement here and say if the len of self.points is less than 2, actually less than or equal to 2, because I believe we need at least 3 points, then I don't want to do any of this. So we're going to say actually the opposite. We're going to say if the len of points is greater than 2, so meaning that it is at least 3, then we'll do this. It's just confusing myself there. We need at least 3 points. So if the line of points is greater than 2, do all of this. Otherwise, don't do it. That should give us the orbit. So let's see now if we're going to get kind of the orbital ring around. Let's run this. And planet object has no attribute points. Sorry, it's not points. It is orbit. And I think I did this right. Self.orbit. Yes, okay. Self.orbit. Nice. All right. Let's see. There we go. Now we get the orbits being drawn as the planets are moving around. Very nice. So, I mean, you can run the simulation as long as you like and see everything working. Now, what I want to do is implement the distance to the sun just to show you that this is not a perfect circle. It is actually elliptical. I know it looks like a perfect circle, but since the scale is so, I guess, small here that we're drawing this at, you can't really see the ellipticalness of the orbits. Okay, so now what I want to do is also draw that distance on top. So to do that, I need to initialize a font in Pygame. So I'm just going to say font is equal to pygame.font.sys font like that. And I'm going to pass inside of here Comic Sans as my font. And for the font size, we'll just go with something like 16. So this is the font you want, and this is the size. Okay, that's how you initialize the font. And then what I need to do if I want to draw the distance is I need to say, first of all, if not self.sun, and forgot we're working in Python, so let's use the actual not, because I don't want to draw the distance between the sun and the sun, which is always going to be 0. So I'm going to say if not self.sun, then we'll say distance underscore text is equal to font dot render. This is how you actually create a text object that you can draw. I'm going to say font dot render. I'm going to do an f string, and this is simply going to be the self.distance to the sun, and then this is going to be in meters. So what I can do is I can divide this value by 1,000 if I want to get kilometers to make it a little bit smaller. So let's do that. Divide by 1,000 in kilometers. I'm also just going to round this just so that we don't get a massive number here. So let's just round this to 1 decimal point, put that in kilometers, and then we want anti-aliasing 1, which is the next argument. And then the last argument, I believe, is the color that I want to draw this in, which we can just make, I guess it shouldn't be self.color. We'll do white. Okay, perfect. So that is now the text object created. Again, you have to use a font object to create a text object, which then you can render on the screen. Now I want to draw it on the screen. So I'm going to say win.blit. I'm going to pass the distance text. And then the position that I want to draw this at is a little bit complicated. And also, guys, sorry, I just realized I made a little bit of a mistake here. Actually, no, maybe this is okay the way it is. When I define x, y inside the for loop, this might be interfering with this, although it didn't seem like it was. So I guess we can just proceed, but I don't like having these names shadow each other. Okay, we'll just proceed for now, but that's kind of what I was realizing and why I paused there. Anyways, what I'm going to do is draw this at x, y, and we're referencing this x, y here, which is going to be the center of the circle. Now, the issue is if I draw this at the center of the circle, since I start drawing the text from the top left-hand corner, you'll see, actually, let me just run the code and you'll see what happens here when I do this. So you'll notice that the actual, the text is kind of at the bottom right of the center. Now, that looks really ugly. I obviously don't want that to be there. So what I'm going to do instead is I'm going to make it so it's drawn directly in the center. Now, to do that, I need to take the x. I need to subtract this from the distance underscore text dot get underscore width divided by 2. So if I take the width of the text and divide that by 2 and then subtract that from the x, that shifts me to the left, so I'm exactly in the middle. And then same thing with the y. So y is distance text dot get underscore height over 2. Okay, nice. Hopefully that is all clear. Now I'm just going to take all of this and we're going to put this below when we're drawing the circle so that it gets drawn on top and we don't have any overlap, or we don't have the circle kind of overlapping the text. Okay, so let's close that. You guys can pause the video if you want to have a look at this. Let's run the code though, and let's see what we get now. Nice. Okay, so now we actually have the text being drawn on top. And for some of the planets, given it is a bit hard to see, but that is all working. Nice. So with that said, I think I'm going to end this tutorial here. This was a lot of stuff to go through. I hope you guys appreciated this and all of the math and explanations. If you did, please make sure you leave a like. Obviously, you can extend this as much as you would like. You can mess around with the scale. You can mess around with the speed. You can change the time step. This is a really, really flexible program, and all of the hard physics and math is done. So if you want to add more planets, you can really easily do that. this is a realistic simulation, something I haven't done on the channel before, and that I hope you guys appreciate. All right, with that said, I am going to end the video. Again, please like the video, subscribe to the channel, and I will see you in another one.